祝你们晚安。
Okay, in this part, I will show you how the 3M system works and what the key features it will bring to us. The first feature is auto-assign master role and slave roles. So, detail speaking, the system will automatically detect the numbers of the power supply and then assign the master role to one power supply and the slave roles to the remaining ones. Even when the master power supply is suddenly off, in case, the system will do the assignment work again. So here you can see the comparison between these two cases. And the second feature is battery charging, control and assignment of the load priority. The system keeps tracking the battery status of the charge and charges the batteries if they are not fully charged. Once the SOC is below specific value, for instance is 50%, then it will cut off all the non-critical loads to ensure the supply for the critical loads and charge the batteries to maintain the system's stability. And the third one is silent mode. It means our system can provide these two modes for user to choose. The silent mode will be used during the night time to supply fuel loads, and all the gensets are shut down and only batteries discharged to supply the loads at night time. The third one is the smart charging and easy plug-in to increase the total power capacity. Actually, it is combined both plug-and-play function and the battery management function. Batteries have to discharge to supply the peak loads when the available power genset is not enough to power the loads. And once the system detects a new power supply is plugged in our system at that time, the new power supply will fully power on to charge the battery and supply the loads at the same time. And then once the battery SOC is 100%, it means the batteries are full charged. The power supply will only supply the load only. So you can see the three cases. Firstly, is only two power supply available, and then at the time the load is bigger than the power output, so the battery have to discharge. But then there is a new power supply is triggered on to join the power supply team. So each power supply's maximum output is 3 kilowatts. So at that time, the battery is not full charged. So the new one have to work under the 4-pot on status to charge the battery and all the loads. And then finally, the battery is fully charged. Then the last one will only output only the value is supplied to loads only. So after knowing how it works, the initial stage we do is to set up the hardware in our lab to conduct some verification tests to prove that our control system can work very well. So please let me to introduce this all these equipments we will use in our lab. Firstly is the lab-based 3 system will consist of 3 DC power supply and 2 units of 100 Ah battery, lead AC batteries, and 1 DC load up to 1 kilowatts. The lab-based DC power supply can be regarded as a combination of AC to DC rectifier and DC to DC converters with programmable microcontrollers, and also some sensors inside. So via USB cable, those 3 power supplies will keep sending the real-time status and receiving control signals from our main controller system. At the load side, the sensors are also connected to collect all the load data and send to our main controllers. So all the current and the voltage values will deliver to our control system for the control system to do some of the process. And then the control system will send a corresponding control command to all these equipments. So the control system is programmed on the LabVIEW platform. Basically, there are 4 parts in the programming process for this system. The first part is the data acquisition and communication. We have tried up to 3 different boards to do the data acquisition and process for our sensor value, like the Fiji board, Arduino board, and the National Instrument DAQ board. Finally, we choose the NIDAQ board because it is very convenient to set any sampling rate you want and any sample mode you want in the LabVIEW platform. In addition, the LabVIEW is able to do the dual communication with multiple microcontrollers. The serial communication is applied in our program. On the left-hand side of the slide, you will see the data monitor interface developed for both NIDAQ and the Fiji board. On the right-hand side, you will see the multiple data communication panel, which allowed us to communicate with our microcontrollers built in the DC-to-DC converters. The second part is the program execution flowchart. So I made this one for you to know how the system works on the different mode and on the different batteries SLC status. The third part is the logic calculation in the program. This logic calculation will determine the power output value for each available power supply on the different numbers of available power supplies. So, literally speaking, it means when there's only one power supply is available in our system, there are 3 cases. So it means I have to do the programming for each case. And then when there are 2 power supplies on, there are another 3 cases. For each cases, you have to do the logic calculation. So totally, and also the remaining one is all the power supplies are on. So totally there are 7 cases. The third part is graphical interface programming. This is the key point. This is the key part of our interface panel, of our interface. It is also the key reason why we choose LabVIEW as the main microcontroller platform. The LabVIEW platform provides lots of graphical functions to develop interface in a fast and easy way. The user can clearly know the system status or values in different ways. Also, the user can easily change the system working mode or any current or voltage value they want to change with just easily swinging the virtual nodes below. Sure. After finishing the programming, we collect all the data and we connect all the data we get from the LabVIEW platform. And we found two issues currently we are faced. First one is the battery transit discharge current, which happens when the load changed but the power supplies are not fast enough to adjust the power supply's output. To resolve this so-called delay problem, we assume to enhance the process time of the system. For instance, we want to increase the read and write speed of the communication with hardware, and we also expect to optimize the logic structure and the calculation. The second concern currently we have is the voltage fluctuation. Because the delay issue I just mentioned in the previous slide, the batteries have to discharge to supply the loads when gensets are not fast enough to react. So the discharge current is almost equal to the increased value of the load. During the discharge process, the battery's voltage will also drop at the same time, which will lead to the busbar voltage fluctuation. Currently, we didn't find any harm that will bring to our system, but once the voltage once we have to do a test for our real equipments, then we assume that this issue could bring some of the hazardous problem to the previous 3M system when the load is up to 10 kilowatts. So basically, the test result proves that our control system can work. So then we use the Honda portable gensets replaced with the power grid to supply the DC power supply. The test results are very good. Also, the same all the results show it is the performance is as the same as what we got before when all the power supplies is connected with the power grid. Now I will introduce you the current and further development of our project. Currently, we still have lots of work to do. Regarding to our system control side, the battery management system may be added, and because of the two issues I just mentioned before in the previous slides. And also we are developing a serial communication toolkit for our own design converters, which will be delivered recently in the next month. And this system will still not integrate the solar energy sources, so because it's still another procurement process. Now, my colleague Mr. Al will explain to you the hardware design.